Hi, thanks for joining. My name is Limor Gulchin, and I will be presenting my recent work with Matt Kussner, Varun Kanade, and Ricardo Silva. Our main interest here is the estimation of causal effects from observational data, with very minimal knowledge of the underlying causal graph. But let's first establish why we should even care about any of this. As an introduction, let's consider the motivation for the study of causal effects. Many areas of scientific study are interested exactly in that. And while the gold standard is randomized control trials, those are expensive, they are hard to design, and they're often morally problematic. Instead, in many cases, researchers have to rely on observed data, whatever is already available to them, as they come to study the effect of interest. One field where controlled studies are hardly feasible is epidemiology, which we unfortunately all became more aware of in the last few months. One of the founding fathers of modern epidemiology is none other than John Snow, which we will consider for the next couple of minutes and is presented here. Snow was a doctor studying cholera for about 2 decades when the cholera outbreak in Soho, London, erupted in 1853. At the time, the leading theory to explain the disease was some unmeasurable pollution in the air, referred to as miasma. But Snow had a different theory he was trying to push forward, and crucially, he collected observed data to back it up. First, he recorded deaths of cholera on a map. The story that follows has 2 acts. In Act 1, he realized the deaths in Soho seemed to be concentrated around one particular water pump on Broad Street. What he was trying to do is draw causal conclusions from only observed data. In other words, he was interested in the effect of improving water quality by, for example, closing a contaminated water pump on the prevalence of cholera. He did manage to be convincing enough to make the local authorities remove the handle off of that particular pump, which reduced the numbers of local cholera cases significantly. But that wasn't convincing enough for the authorities or the scientific community, and the outbreak went on across the city. If he could randomize the removal of pumps, he could actually say something about the prevalence of cholera given some intervention on the water quality. But unfortunately, that wasn't so easy. Let's just focus on this for a second. If he could randomize the removal of pumps in different locations, represented by lightning strikes on the map presented here, this would correspond to changing the graph from G that we've seen before to G prime, with the edge removed from U to X. Given this randomized data, we could actually make a causal claim, as Snow tells us in the slide. However, Snow can't actually improve the water quality because he doesn't have any proof that this would help. It could spend money needlessly and even put some people in actual danger. The authorities would not hear of it. So he can't actually get to this altered graph G prime, and he has to rely on whatever he could get from the original graph G. But he did not give up. He wiped away those tears and collected more data. In the second act of the story, Snow collects more data from across London, but this time also marks down the water provider to the sub-districts where the deaths occurred. He found, remarkably, that one water supplier had many more deaths associated with it. But even more interestingly, in many sub-districts, both suppliers were present, often arbitrarily, in one side of the street versus the other. Fortunately, in this particular case, water suppliers essentially conducted a randomized natural experiment, as water supply was independent of location, socioeconomic status, or any other possible confounder of observations. Essentially, people get their water supply only from these companies, which have different water qualities but are randomly distributed, which is actually just like if Snow could randomize X. Today, we would call such a factor that acts as a coin flip in a randomized experiment an instrumental variable. But this is a rare case. We almost never get so lucky with observational data. In this work, we will be considering what we can still do when we don't get so lucky. Generalizing a bit more, let's define the causal effect of interest in this work, the average treatment effect, for another problem of interest, the influence of diet on cancer. The AT will tell us how the expected value of an outcome of interest Y, in our case cancer, will change if we intervene and set the value of a treatment X, in our case diet, to some fixed value. Let's call it little x prime, that will stand for vegetarian diet, against some other fixed value, little x, say meat-based diet. If we have no confounding present, we can uncover causal effects simply from the regression on observed data, cancer Y on diet X. When we do have confounding, like through income or even the unobserved latent feature genetics, Not all is lost yet. If we control or adjust only for the confounding elements between cancer and diet, in this case income level, we could recover the causal effect by including that in the regression. However, we should be careful not to include height, as it would bias our estimate, or in deseparation language, it would open the currently blocked path, which includes genetics. As long as we know the causal graph, we can apply existing graphical criterion, the backdoor criterion, to get the valid adjustment set that we will need to control for. Pearl has formalized both the graphical definition of such adjustments and also how to apply them in practice via the backdoor adjustment. However, if all we have is a dataset with observed features and not much else, any feature in the dataset might be related to any other, and there might be some unobserved latent variables as well. So it's no longer that easy. In our proposed method, we will consider, first of all, two possible reactions. One natural idea would be to try and identify the full causal graph so we can apply the existing backdoor criterion to recover the causal effect. However, this solution would involve an expensive combinatorial problem, which will only give us a Markov equivalence class of graphs and will diminish in power as dimensionality grows since it relies on multiple independence tests. The good news is, this is actually a harder problem that we need to solve. Instead, we can target the adjustment set directly. That would actually give us a fast, gradient-based optimization problem that will make the adjustment identifiable with few assumptions and reduce the number of independence tests that we'll need to carry out, which would allow us to retain higher statistical power. Building on top of work by Entner et al. From 2013, we convert the backdoor criterion from a graphical one to an independence-dependence-based one. However, Entner et al. Still proposed a hard combinatorial problem that requires iteration over possible subsets of covariates Z, which they suggested to solve with random or greedy search. It is important to note that their solution also introduces an auxiliary variable W that will function as an instrumental variable conditioned on the adjustment set Z star. However, as dimensionality of the dataset grows, this method will actually blow up. We extend Entner et al. By proposing a continuous relaxation, suggesting to learn a function phi over covariate Z that will identify the valid adjustment set Z star for us. We essentially replace independent statements with statements that minimize or maximize dependence, and then add sparsity as well. The sparsity of the learned functions will assure us that out of the possible equivalence class of phis we might learn, the sparsest one will actually give us a valid adjustment set. We can turn this problem into an objective function via Lagrangian formulation and obtain this final form. We tested the performance of the method on a simulation in which we will be considering this experimental setup. Z3 would be a valid adjustment, but inclusion of Z1 or Z2 can actually harm our estimation by opening a currently blocked path. We will be also comparing against all possible baselines that have as weak of assumptions as ours, Entner's search algorithm, and two naive baselines that would just include all Z or no Z in the adjustment set. We will be considering 4 simulation setups in total, varying between high and low causal effect and high and low variance of the noise term in the equation generating X, and we expect them to make different methods suffer more or less across them. So it is a way to check the robustness of the method. I'll briefly show the results in these histograms where our performance appears in blue at the bottom. You can see that we outperform or at most compare with one of the baselines for each one of the settings. For more, let's discuss in the poster session, or you could refer to the paper. Finally, we also applied our method to a real-world data set, but I'll leave these results for the paper or discussion as well in the sake of time. In conclusion, in this talk, we considered first the importance of causal effects and the strong assumptions it usually takes to recover them. Next, we also considered what we can still do based on observational data alone and saw that existing methods involve solving difficult combinatorial optimization problems. And finally, we proposed a continuous relaxation of previous work that leads to a fully differentiable optimization that can be more readily solved by modern auto-differentiation software. Thanks for watching. Full paper can be found in the link provided here and also as part of the coming AI Stats conference. Please check out the poster session if you're interested. Thanks.